Yep, it's okay. Good. Yeah, I did a poll at the end of last week, and the majority said that they quite liked the music in the background, so I'm sticking with it. Let's get cracking then. Half-Life. Anyone want to define Half-Life for me? I know there's A-level students here, so if you're an A-level student and you're partway through typing your answer and I've managed to catch you before you've hit enter, don't hit enter. Let some of the GCSE students maybe say what they think. So hopefully that message gets to you before you hit enter, because there is, of course, a delay, latency. I know there are GCSE students out there watching this. I'm watching you. Join in. What do you think Half-Life is? A-level students, you probably know this. Give it a few moments, and if I haven't got answers from GCSE students, well, I'll get the A-level students in. I can see at least one GCSE student is typing an answer to what they think Half-Life is. That's good. Doesn't need to be a long answer. Doesn't need to be a long definition. Okay, so we've got two answers there so far. We've got 𝗭𝘪𝘀𝗲 saying the time period for 50% of the atoms of one element to decay. Okay, A-level students. Some of you know me quite well. You've been tuning into this for quite some time. Others know me more personally than that. A-level students, reading 𝗭𝘪𝘀𝗲's answer. I'm sorry if I'm picking on you a little bit, 𝗭𝘪𝘀, but it's okay. That's what we're here for. It says the time period for 50% of the atoms in one element to decay. Correct 𝗭𝘪𝘀. Silver, so A-level students, go ahead and correct 𝗭𝘪𝘀. Silver's, your answer, so the time it takes for an element to decay, the time for an element, well, I don't know what you mean, basically. An element to decay doesn't make a lot of sense. You might be talking about the atoms within a substance that are a particular element, but even then, the duration of decay is, we take that as instantaneous. The decay instantly happens. The question is, when does the decay happen? So your answer is a little bit too vague there. Intel, you've said the time for half of an unstable nuclei to decay. So this is going to sound like I'm being ridiculously fussy now, but how does half of a... oh, you have said nuclei plural, so maybe I shouldn't be fussy. Yeah, actually I think that answer's okay, Intel. I think that's fine. Full marks for you. Gnome has said time taken... Have you changed your name, Gnome? I don't recognise it. Anyway, it says you're a regular... Oh no, you're just a normal participant. Okay, join in next time and you might become a regular. So Gnome, time taken for the number of radionuclei, I love that word, of a sample to decrease by half, or indeed to half. I suppose that's the same thing. Yeah, I like that, Gnome. That's good. So Lex has said the amount of time it takes for substance's mass to decay by half. Yeah. So there's two different ways of quantifying the amount of substance, Lex. One is mass. One is the number of what depends on the substance, the number of particles, let's say. So if we're talking about a metal, we can talk about the mass of the metal, or we can count the number of ions within that metal. There are two different ways of quantifying the amount of substance. And it's the same with a gas. Let's take nitrogen gas. We can count the number of molecules, or we can count the mass of the gas. Or I suppose indeed when it comes to gases you might have heard of moles, but that's just another way of counting the number of molecules and giving it a different number. So you've said the time it takes for a substance's mass to decay by half. The mass of the substance won't change overall, not really, not by any measurable amount. What's happening is within that substance, the nuclei of the atoms, if it's a radioactive substance, they're unstable. And so the mass of the substance, it says the time it takes for the substance's mass to decay by half, is a little bit woolly. You could say for the mass of a substance to halve by radioactive decay or something like that, but the mass itself doesn't decay. The mass is still there. So the mass of the radioactive substance. So you end up with a substance containing half of the original radioactive nuclei, and half of the nuclei in that substance are some new nucleus, some new nuclei, whatever the daughter of that decay would be. So actually not a bad answer. I'm being ridiculously fussy, which is okay. So no one picked me up on the thing I noticed. The thing I noticed, by the way, and I'm just going to scroll back up on the chat. Hopefully it will scroll up on the chat on your screen. Back here. The time period, Dvorak said. Time period is a technical term. In terms of oscillations, it is the time between 2 points on a wave of the same phase. So the time period here is a technical term we shouldn't be using. So rather than saying time period, you could just say the time for 50% of the atoms of one element to decay. There's nothing wrong with that. Yeah, so Pranav's answer there is absolutely super. I like Pranav's answer there. Look, we're getting involved. I like this. This is really good. So under the let's consider half-life then. If it's the amount of time for half of the nuclei, the radioactive nuclei in a substance to decay, then 2 half-lives is how long it takes for half and then another half of them to decay. I'm going to draw a picture because I'm not doing a very good job of explaining it. Here are 4, it's just 4, it's not very many, 4 radioactive nuclei. In one half-life, 2 of them pop. They have decayed. They have now decayed. They're still there, but they're not the same element as they were before. That's in one half-life. Maybe a half-life's a year. So 1 year later, I've only got 2 of these nuclei. Another year later, I'm not going to end up with 0. I'm going to end up with 1. You just halve it each time. So in one half-life, I have, let's do a little table here. So in one half-life, this is number of half-lives. Number of half-lives. In one half-life, I have, and this is going to be proportion. I can't write. Proportion. We're going to have a half of the original radioactive nuclei remaining. How many are we going to have after 2 half-lives? So we had half left, half already decayed, they're not going to come back. Half is left, 1 half-life later, what have I got left? Quarter, dead easy, thanks Pranav. And after 3 half-lives, what are we going to have then? Let's leave this one for a GCSE if you get a chance, but I might not have got that message out there in time. Intel, great. 1/8, that's super. And just for luck, let's do one more. After 4 half-lives, how much of the original radioactive substance will be remaining? Whether we do it by counting mass, counting number of nuclei, how much will be left? 160. So in each of these cases, what you're doing is you are multiplying by a half. To get from half to a quarter, we multiply by a half. To get from a quarter to an eighth, we multiply by a half. To get from eighth to a 16th, we multiply by a half. Dvorak's written 1 divided by 2 to the power of number of half-lives. Yep, you're absolutely correct. Dvorak spotted it. You're supposed to notice then this is 1 to the. So this is 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8, and so on. Sometimes we'll write that as a half to the power of n, where n is the number of half-lives, because that's a little bit more intuitive for students to see. What we're doing there is multiplying by a half n times. So we originally had 1, the full amount of the substance, 0 half-lives, and then 1 half, 2 half, 3 halves. We've multiplied by half 3 times. So you end up with that. Right, now, that's all very well and good, and we can do some nice easy calculations with this. We can say, for example, that if I have 10 grams of a substance with a half-life, and I will write this down like this. Let's say the original mass of the substance is 10 grams, and its half-life, that's a T for time, with a subscript half to indicate half-life. Let's say it's 10 years, like that. And then we can say something like, okay, well, how much of the substance? GCSE students only, please. A-level students, you'll get your chance. We can say how much of the substance in, let's say, 5 half-lives. So in 50 years. So what would we have? Now, GCSE students, you can perfectly happily get the answer by taking those 10 grams and halving it 5 times. No reason why not. What else could you do? So I'll leave you to do the calculation. 𝗬𝘂𝗲, well done. Yep. That is, I mean, we need a unit on that. Hang on. No, your second digit is wrong. If you typed it wrong, I just looked at the first digit. I was being sloppy. Yeah, I think you might just copy the number wrong off your calculator screen. Because those are 3 numbers I can see on my calculator screen, but we're missing one. So I think it's just you've copied the number wrong. Any other GCSE students out there that have got it? What we're doing is 10 grams, original mass, multiplied by 5 half-lives. So that's a half to the power of 5. And you get, just as Lex has got with the unit, 𝗬𝘂𝗲's, your number is different again. Interesting. 𝗬𝘂𝗲𝗲's got it there. So I got 0.3125 grams. So, 𝗬𝘂𝗲𝗲's, while I'm talking, do you mind typing out a description of what you did? Because that's going to help us unpick where you've gone wrong, I think. The nice thing about this formula is that you can use non-integer numbers of half-lives, which you can't do if you're just halving 5 times. You do have to be careful how you enter it into your calculator. Right, okay, 𝗬𝘂𝗲𝗲's, let's go through it step by step. So, if we've got 10 grams, that's with 0 half-lives. Then 1 half-life, I have 5 grams. 2 half-lives, I have 2.5 grams. 3 half-lives, I have 1.25 grams. Okay, super. Yep, 4 half-lives. I don't think I need to finish off, do I? Although I feel I'm one of these people that doesn't like leaving things, so I am going to finish off. So 0.625 grams. And then, as 𝗬𝘂𝗲𝗲 has correctly said, 5 half-lives, we half it again, 0.3125 grams. I mean, you could actually do that without a calculator. But what you can't do without a calculator, not accurately, is exactly the same problem. So, my original mass of my substance was 10 grams, but this time, and the half-life, by the way, is still 10 years. And I'm in the same substance, so it's got the same half-life. But this time, I'm saying, well, how much substance is left when I have left it for 45 years? Now, that's not an integer number of half-lives. So, GCSE students only. Again, A-level students, you'll get your chance today. GCSE students only. Just tell me what you get, and then we'll talk about how you get it. And if you're thinking, actually, this is quite tricky, yeah, this is something that students do find difficult, so you're not alone. Don't be really put off by it. Don't think, oh no, I don't get it. It's okay. So Dvorak, your answer seems an order of magnitude out. I like Lex's answer better, and there's the unit. Yeah, I like Lex's answer. Lex has got it right. Dvorak, yes. Yes, very, very important. So let's go through how we calculate that. We've got the original 10 grams, but then we multiply it by this factor, a half to the power of the number of half-lives. But it's not an integer number of half-lives. So how many half-lives is it? Well, it's the amount of time, 45 years, divided by how long each half-life is. So this is time. I mean, I could write down if you wanted. This is going to sound nonsense, but I could write down 45 and then this is time per half-life. And of course, I mean, that's going to be impossible to read. That is too small. The times will cancel, and because this is on the bottom, it goes back up there again. So we end up with 4.5 half-lives. Maybe just ignore that, because that's crossing things out, because that's probably confusing things. You can see that 45 divided by 10 is the number of half-lives, 4.5. Chuck that into your calculator. It gives you the answer that you can see in the chat there. I don't need to write it down. And that fits in. I will write it down because that fits in. 4419 grams fits in nicely between 4 and 5. But you'll notice it's not halfway between 4 half-lives and 5 half-lives. What is exactly halfway between 4 half-lives and 5 half-lives? Okay, I'm not saying what's 4.5 half-lives worth. I'm trying to say what is the amount of mass exactly halfway between 4.5 and 5. 4 and 5 half-lives. I suppose what I'm saying is what's exactly halfway between 0.625 grams and 0.3125 grams. Yeah, now this is where A-level students are going to start to shine now. Okay, so if we had a mass of the substance exactly halfway between 4 and 5 half-lives, that would be 0.468, let's have it all written out, Wombat, there's no reason why not, grams of the substance. And we know, what do we know? We know that a half-life is 10 years, and we know that the original mass was 10 grams. So here's the question: how long will it take to get this mass? That's still a GCSE question, but it's a really, really tough one. So A-level students, feel free to join in. Wombat's already written an answer, I haven't checked it yet. Feel free to join in. In fact, this is not GCSE level. This is now, we're entering A level. If you're looking at it thinking, well, I have no idea how to do that, this is, you know, this is more tricky. It uses something which I think you learn about in GCSE maths, but maybe not, because I really am not a maths teacher. Pranav's corrected Wombat there. So one way you could work it out if you were a GCSE student is by trial and error. Nothing wrong with that. You don't have to try too many times to get a two significant figure answer. Starting from 4.5 half-lives. Oh no, it needs to be a little bit less than that. Let's try 4.4 half-lives. Super, I've got the answer. That's okay. But you can see the A-level students have done something a bit more. Yeah, Noma's got it. So this is what A-levels students might have done. They've looked at that and they have rearranged the equation in order to calculate n. Now what we could do is we could just put numbers in here. This is going to make it a little bit nicer for GCSE students to look at. But what we've got here is the new mass equals the original mass times by this factor. Whatever this factor is. The new mass is 0.46875 grams equals the old mass, which was 10 grams, times by a half to the power of, or I could call that 0.5 if I want, 0.5 to the power of n. So GCSE students, you can tell me now, because I can't remember, and A-level students, because you've only just done GCSE, you can tell me, because I don't know, do you do logarithms in GCSE maths? Nope. Okay, no logs in GCSE. Look at that. Well, let's teach you something new then, because it's good fun. First of all, let's get rid of this 10. GCSE maths, I know you've got that. How do I get rid of this 10? I just want a simple equation. What's the first step to get rid of this 10? Not even further. Okay, that's okay, James. Not a problem. Why isn't my rubber working? Oopsie. 0.5 n. How do I get rid of that 10? Come on, GCSE students. I want to get the n. How do I get rid of the 10? So I've just got something much more simple. Right now, n is the power of 0.5, and then it's being multiplied by 10. Divide both sides by 10. Super. Well done, Silvers. So this becomes 0.046875, and that equals 0.5n. And here's the new bit. Here's the new bit. Log of 0.046875, you can see that decimal point, log of that is going to equal n multiplied by the log of 0.5. Your calculator, you've got a little button that says log. So you can now do n is equal to log of 0.046875 divided by log of 0.5. There you go. And it'll give you their answer. Is that what you did, Wombat and Pranav? Because I'll tell you now, I've asked A-level students this sort of thing in the past. Yeah, well done. I have asked A-level students this sort of thing. Use log base 2. Fair enough. No reason why not. I haven't said what base to use. I think it's the same approach, Gnome. I do think it's the same thing. Yeah, I think it's the same thing. I haven't said what the base of this log is. No, exactly, James. You're exactly right. It doesn't make a difference. So GCSE students right now are thinking, what? It really doesn't matter. You're essentially using the laws of logs. It's a different way of writing the same expression, and you've got that to look forward to when you do your A-levels in maths, apparently, because apparently you don't do it in GCSE maths. But never mind. Right. That's Half-Life as far as it gets at GCSE level. And if you're a GCSE student and you think, right, I don't want any of the A-level stuff, then what I would ask you to do, I've set an assignment on Isaac Physics. If you want to carry on doing this stuff, the first 3 questions of this assignment are all GCSE level. The next few are A-level. To find the assignment, you have to join that Isaac Physics group. So go to isaacphysics.org, make an account if you don't have one already. And then below, if you can see, there's the link below here on Discord. If you hit that link, then you can join the group. You can join the Isaac Physics group, and it'll be set there as an assignment. Oh, look, we've got somebody else who's joining. Super. Let's manage user, participant. There we go. I'll welcome them later. So if you're a GCSE student and you just want to practice some of those questions we've already looked at, there's where you can go to do that. Stay on the line. If you get stuck at any point, get back on Discord. I'm here until 7 o'clock. Ask your questions and I'll help you. It becomes a bit more of a to and fro, a bit more of a tutorial. If you're still there on this line because you're an A-level student, then that's all good. We're going to go a step further. And because I can't assume you know stuff. Yeah, okay, so it's the same approach, one back. Yeah, it's the same approach. So here we go. We've got... Did you type that a minute ago? Oh dear, that's the first time Discord has been that bad. Let's just click that there so it doesn't say that there's a message waiting. Okay, so... Oh dear. So here we go. First things first, radioactive decay is exponential. What does that mean? That means that if I drew a graph, you probably already know this, but I'm not going to assume you know this. If I draw a graph of, let's say, number of nuclei, I'm going to call them N, that are radioactive versus time, then I end up with this sort of curve that does this. But this curve has some very special properties. Here's one of the properties. One of the properties is that the gradient of this line, it depends on the value on the y-axis at the point where you make that measurement of gradient. So you'll know as A-level students that if you take the gradient of a line where it's a curve, then it has different gradients all the way down it. I mean, what's happening to the gradient as time increases here? Chuck it into the chat. What's happening to the gradient as time increases? You say it's decreasing. Tends towards 0. I like your answer, Pranav. Gnome says it's less, it's decreasing. But it's negative. Doesn't that mean it's increasing? The magnitude of the gradient is definitely decreasing, becoming less negative. Yeah, exactly. So if I took the gradient at any point, let's take the gradient here, I'd have to draw a tangent. And then I'd say that's the gradient at that point. And what you'll notice is that's quite a high magnitude of gradient at a high value of n. I hope you can see this red ink. At a low value of n, we end up with a low. Let's do it down here. We end up with, come on, a low gradient. Just like that. So there's a relationship here, and what's special about this relationship, these exponential relationships, what we're talking about, is that the gradient, the rate of change of the y-axis divided by the x-axis, is proportional to, I'm going to put a minus here because this is a negative gradient, but it's proportional to n. Okay, we could put the minus here and say, look, it's a negative gradient, the rate of change is negative, and that's proportional to a positive n, so that's why you end up with the minus there. But I'm going to put the minus here just because it's a little bit neater. Now, some people have seen this sort of approach I'm about to do many, many times, and it's certainly not the first time I've done it on Physics with Keith. So what I'm going to do is, first of all, get rid of this proportionality, replacing it with a constant of proportionality. That's now equal to minus lambda n, just like that. And the next thing I'm going to do is say, well, look, it's a constant curve. It's not stepping down, it's constantly changing. And so I have to smooth out these large changes by making the interval as small as possible, infinitesimally small. So my deltas become d's, and we end up with dn by dt equals minus this constant of proportionality multiplied by n. That's a differential equation, and it's one of the standard differential equations that A-level students, even if they're not studying maths, ought to be able to solve. First thing you do is you gather together your like terms. So I'm going to divide through by n, and I'm going to multiply through by dt. And I'm doing that so that I get my dt's away from my n, but all my n's together. And the next thing you do is you see this is a tiny interval of n, and this is a tiny interval of t. So I can add up all those tiny intervals. I can perform a sum, a special sort of sum called an integration. And it's summing a continuous change. Now what I've done in this step is minus lambda as a constant. It doesn't depend on t. So I don't actually have to do minus lambda multiplied by this little bit of t, then add it to minus lambda multiplied by the next little bit of t, then add it to minus lambda multiplied by the next little bit of t, then add it to minus, I suppose you hopefully can see where my red dot is moving around. I don't have to do that. I can make it easier. Just add up all the little bits of t and then multiply it by minus lambda, because minus lambda is a constant. And this right hand side becomes even easier, because if I add up all the little bits of time, I could just call that time. The time from when I had the very start, whatever this original number was, I don't know, let's call, whoops, didn't mean to do that. Whatever this original number was, let's call that n0. The time from n0 to whatever point we're interested in knowing how many nuclei there are. The last step is this bit here. Right, this is an identity, and I've proven this in a video, and I recorded that video because I can never remember how to prove it. So if you go onto the Physics with Keith YouTube channel, you will find the videos on calculus, and in one of those, I think it's 12 videos, and in one of those, it derives this expression. I think it's in the video for miscellaneous uses of integration. But this is an identity. It's just going to be the natural log of n. But there's a bit missing. Something missing in this whole equation. Who wants to tell me what I've not included? Out there will be A-level physicists, A-level mathematicians who are watching this and thinking, oh, hang on, you've just done an integration. You've forgotten something, sir. What have I forgotten? Thank you, Wombat. Thank you, Pranav. Yep. Constants. Integration constants. So I could say add some constant. I don't know, let's call it C1. And add some constant. I don't know, let's call it C2. I don't like having two constants. I'm a simple man. I don't like having two constants. So I could gather those constants together. I end up with minus lambda t, and if I subtract c1 from each side, I can end up with c2 minus c1. And look, a constant minus a constant is just a constant, so let's just call that plus c. Great. The next step, when you've got, and this is the same approach you'll use when you look at capacitor discharging, when you look at lightly damped harmonic oscillators and the amplitude of them, when you look at cooling curves for transferring thermal energy. This appears all over physics, is we're going to raise e to the power of this equation. Look, this left-hand bit is equal to this right-hand bit, so e to this left-hand bit is equal to e to this right-hand bit. And e is the inverse function to the natural logarithm. So e natural log n is going to equal e to the minus lambda t plus c. E to the natural log of n is just n, because they're inverse functions of each other. And this part here can be split, and it can be split because of the laws of logs. Look, 10 to the power of 2 plus 3 is equal to 10 to the power of, I suppose 10 to the power of 5. I don't know why I wrote that, I'm not sure how that's actually helping. Which is the same as 10 to the power of 2, 10 to the power of 3. Have I gone off the edge of the screen there? Yep, thanks Pranav. Not a problem. I have the technology. Look at that, sideways. So 10 to the power of 2 plus 3 is equal to 10 to the power of 2, 10 to the power of 3. So using the same principle, just with a different base, it's base e instead, but it's the same principle, we end up with e to the power of c multiplied by e to the power of minus lambda t. Well, okay, what on earth is this e to the power of c? If c is a constant, which it is, and e is a constant, which it is, Euler's number, then e to the power of c is a constant. But what does this constant mean? Well, this constant equals n when this term is equal to 1. And this term is equal to 1 when t equals 0. Because when t equals 0 minus lambda t equals 0, e to the power of 0 is 1, because anything to the power of 0 is 1. Except maybe 0, or maybe it is, or maybe it's not. I'll leave you to look at the various YouTube debates about that one. I'm not getting into that. I'm not a mathematician. So, e to the power of c, I'm going to call that n0. The number we had, what n equaled when t equals 0. And that's it. This is our expression. Math error. This is our expression. And now what I'm going to do is I'm going to show you a drill spreadsheet which writes it in this form. Just writes it in this form. When this fraction here is equal to a half, the time is a half-life. So you can use this to see what the relationship is between t, when it's a half-life, and lambda. I'll save you the bother. I'll show you what it equals. T a half is equal to natural log of 2 over lambda, and lambda equals natural log of 2 over the half-life. But these are the two equations we're going to use. So, that was me talking for far too long. Here comes the drill spreadsheet. I said it was rough around the edges. It's not a pretty one. The yellow box is the missing variable. And if I hit F9, it will give me a different question with a different missing variable. You'll notice this number's quite small. Could you tell me, are you able to read the number that's written beneath the lambda symbol? Or is it too small? If it's too small, we can abandon this and I've got other questions. This drill spreadsheet is also available for people who are regular participants. You can, good. The reason why it has so many significant figures is because that's one of the values that are calculated. Yeah, well done. That's one of the values that are, thank you, Pranav. That's one of the values that are calculated. And so because the way these sheets work, I don't want there to be rounding errors. I just thought, I'll just show all the digits. So you wouldn't give an answer with that many digits. If I hit F9, I get a different question. Hit F9, I get a different question, and so on. So, the number beneath the term is what the value of the term is. And you can solve this any way you like. We'll start with this one. You've been given a half-life, 730 microseconds. This is the half-life of fermium-27, I can't even read numbers, 241. So what is the decay constant, lambda? See if you can calculate it. Chuck it in the chat as soon as you're done. You're A-level students, you might as well race against each other, have some fun with it. Always worth double checking. I know you were in a rush because you wanted to beat everyone else, which is fine, I get it. Well, you don't have to use half-life. You could solve it without using half-life. No reason to use half-life. Fascinating. Okay, so if you use half-life, this is what's interesting about this. it makes me think there might be a problem with this. If I use half-life, if I do the natural log of 2, I'll then divide that by the half-life, 730 E6 minus. It does actually give me a slightly different number. So this is obviously heavily rounded, and yet these aren't. That's an issue, isn't it? I'll have to look at this sheet. Yeah, it gives you more like 950. So, if this was an exam, for example, any number between those two, actually probably not any number between those two answers would be acceptable. And you can see the effect now of having a 2 significant figure value here. So you would have to round your answer to 2 significant figures, and it gives you different answers depending on whether you are using this equation and the numbers given, or just using natural log of 2 divided by the half-life, which I think is interesting. This sheet, by the way, says it should be that number, so it uses those in the calculation, not the half-life number, which is interesting. Unless I'm doing something really, really stupid. Natural log of 2, 730 E6 minus, divide. No, I agree with you. Wombat, I agree with you. So sometimes on mark schemes, you'll see that more than one answer is allowed. And that's because when we're dealing with numbers like this, rounding plays a big part in what the final answer is. It really matters. Right, let's have another look at the next one then. So, boom. Yeah, I can only think of one way of doing this one. Making people a while to type things into their calculator, but okay. I can't actually see the numbers because my eyesight's not great, so... I'm going to have to get closer. It does look weird, doesn't it, Wombat? 104.996.02 43 4.3499E 10 minus multiply sine. Well, I didn't get that, sir. I didn't get that, Wombat. I got, well, yeah, I got what you got the second time round. Yeah. Yep, exactly what I got, James. Gnome, I think your answer is similar. I'm not sure why your answer is different, but let's bear in mind that all calculators approximate exponentials. They don't calculate an exact number. So it may be that your answer is right on your calculator screen. It's certainly close enough. Let's see how Excel calculates it. Oh, look, 99%. 2 significant figures. Well done. And so on. So I said this one was rough around the edges. Should we look at a different set of questions then? So you can practice that. That's on the regular participants Discord channel, all those questions. There's another resource, the 99 Problems Work Booklet, the PDF of which you can get for free. I'm now going to chuck up a question. I'm going to go to question 67. Sounds like an odd one, but there's a good reason for it, because that's where Half-Life stuff begins. So here's 67, and here's a pretty typical question. I might have to just make it smaller. Oh, just fits. Look at that, just fits. Okay, pretty typical question. Let's see how you fare. Let's all start with the decay constant. Okay, so I think we need to be quite careful about units here, don't we? I think we have to be quite careful about units. The natural log of 2 has no units. James, you haven't given a unit for your answer. Pranav, I like your answer the most. Gnome, I like your answer the most. I mean, of the two of them, if I had to say which one I'd prefer, it would definitely be Gnome's answer. Although, actually, Gnome, your unit is wrong. So, you're both falling just a little bit short, but in two different ways. So, right, can we see what's wrong with Pranav's answer? Yeah, not the -10. No, the -10's okay. This number here is to 4 significant figures. Okay, you can see that. That's 4 significant figures. That is the only datum in the calculation. So when we did our calculation, let's get a blue pen. When we did our calculation, we said, oh, okay, the decay constant is equal to natural log of 2 divided by the half-life. The natural log of 2 has no units, so I'll just write that as it is. It's just a number. The half-life is given as 1.277 times 10 to the -10 years. Yeah, I wouldn't bother turning it into seconds. I really wouldn't. There's no advantage to that, I don't think. So let's just carry on with this. So, if we want to know what lambda is, we just chuck our numbers in the calculator and we get, as you've already said, you get 5.428. 5.428, which is what Pranav has said there. No, you need to watch that last digit. The digit after it is a 9, so you shouldn't give it as a 7. Times by 10 to the -10. And look, years is on the bottom, so that's years to the -1 a year. Now, I'm going to ignore this bit here. It's mean life. That's not something that appears in A-level specs, so we're going to completely ignore that. No, we're here to learn, Gnome. It's all good. So we're not going to look at mean life. That's nonsense to us. And instead, we're going to look at, if we start with that much potassium 40, how many grams will remain after that many years? It's a +10, not a -10 power. No, it's a -10 power, Pranav. Oh, that's 9. You mean there? That's not a 10 at all, that's a 9. Yeah. No, I don't mind at all, Pranav, not at all. So Wombat's got an answer. We've already tried this sort of question before. Gnome has got an answer. We've tried this sort of question before, so we've got a good feel for how to do these sorts of questions. Yep, so your answer would be given to 3 significant figures. Why? So Wombat's given your answer, Wombat, is to 3 significant figures, but Gnome's answer is to 4 significant figure. So why did Wombat give 3 and Gnome go 4? Which one's right? Yeah, it is a mass. But why is Wombat's answer correct? Gnome, you've changed it. Yeah. Yes, exactly. We have a 3 significant figure mass. 3 significant figure mass. We give our final answer to 3 significant figures. Even though that's 4 significant figures there, it doesn't matter. Right, let's look at... Yeah, we've got enough time. Let's look at one more. I don't know if this has been helpful at all. It's always good to revise this sort of thing, though. Oopsie. Let's just put the next one up. So we might as well look at number 68. You can't practice physics too much. That's the bottom line. As I was saying to my class that I teach capacitors to just recently, what is the mean life? Look it up, Pranav. I can't remember. I haven't taught it for ever. I've never had to teach it. I can't remember what it is. There's another thing called lifetime, which is not the same thing as half-life. And I'm wondering whether mean life and lifetime are in fact the same thing. But I can't remember. It's always good to keep practicing. As I was saying to one of my classes I teach capacitors to, that's the area of the course where I consider myself weakest. And I'm fairly good at physics, I like to think, but that's the area of the course where I consider myself weakest. So I went away and I brushed up. I did some more reading. I did some more question practice until I'm less weak. That's how it works. Until next year when I've forgotten it again. So how are we getting on with this? Decay constant. While I've been on the air today, I have had 4 people request to become participants and made participants in real time. This is super. So, yeah, there's no advantage to sticking it in seconds. That's a bit of a dopey move, I think. So you've kept it in years, which is sensible. You've given your answer to 2 significant figures, and I'm wondering why. Why have you done that, Wombat? Okay, 3 significant figures. I'm still asking why. It is known, but we haven't used that number in the calculation for part A. Or have we? Oh, we have! Oh, I'm talking nonsense! Oh, how embarrassing for me! I'm talking absolute nonsense! You did! Of course you have! Yes, thank you for correcting me, Wombat. Yeah, of course you have. Oh, my sincerest of apologies. In which case, should be 2 significant figures. Absolutely it should be. Gnome is correct, and you were correct first time round. Absolutely right. So if we want to figure out the decay constant, we have got, I'll just work through it together, the mass is going to equal the original mass multiplied by e to the power of minus lambda t, which I think is what Pranav's put there, but just gone off the edge of the screen on the what's it called down below, the little embedded stream. So what can we do? We're trying to find what lambda is, so we can rearrange the equation to get lambda as the subject. I mean, I'm pushed for time now, but you're all getting the right answer, so it looks to me like there's no issue there. And then half-life, once you've got the decay constant, half-life is trivial. It's natural log of 2 divided by that. Super. Now, are there any questions? Are any GCSE students who are working on... I'll check what your answers were, by the way. Yep, 5,700 years is correct. Well done, Wombat. How would you do that, James? I suppose you could... I'm curious to know how you would do that without messing around with the equation in the first place. I suppose you could. Yeah, exactly. So that's what I was thinking, James. I suppose you could. We'll try it. Oh, I haven't got time. Try it. Let me know, James. I'll leave this chat open. Feel free to let us know later if it makes a difference. I'd like to say it doesn't, but we saw from the previous example that sometimes you get numbers that are similar but not quite the same depending on what you do, simply because of how severely rounded these numbers are. So we'll see. Right, I'm out of time. So what I wanted to show you was two things. The first thing was the homework, which is that task that I linked earlier on in the Discord chat, and I'll put that link just again into the Discord chat. If you're not on the Isaac Physics group for this and you want some homework, why wouldn't you? Click that link and then join the group, and the tasks will be there. You can just go ahead and complete those tasks. The first three here are GCSE. It then goes a little bit more tricky after that. You'll notice that the third one of this is labelled GCSE C1. That means it's considered challenging for GCSE students. So if you're finding this particular question challenging, don't worry, good company. A lot of people have. Why don't you ask us for help? Pop it into Discord. It's all what we're here for. And the other thing I want to show you is this. The website, which most of you know about. If you click events, then you will see the current schedule. You'll notice that there's a bizarre gap between the 14th and the 28th. Now, I'm no expert in the 7 times table, but one might expect a 21st of September in there. But no, I have an appointment to have my flu vaccine then, so I'm afraid I will not be available. So next week there is no Physics with Keith, but feel free to join in on Discord anyway. Pop things into the questions and answers team. Not team, that's Microsoft Teams. Channel. Pop things into the questions and answers channel. And then we'll be back in a fortnight for Penetrating Power. We're going to start again with some basic GCSE stuff, but that won't be for long, because then we're going to go into some much more in-depth work looking at penetrating power for alpha, beta, and gamma radiation through different substances, and it's going to be at A level. It relates to a required practical that can be done. The other thing I'll point out is that if you go to videos, people sometimes say to me, "Sir, have you done a video on this or that?" Well, have a look. They're all here. You can see if I've done a video on this or that, including a bunch of Isaac Physics videos. I was commissioned to do some videos for Isaac Physics. These are all on there as well, with permission from Isaac Physics themselves. And if you want to look back at any of the old recorded tuition sessions, these are here too, including season 3. Oh look, radioactivity. So if you want to look back at how I did it last time, it's there as well. And that's all I have to say. So thank you very much everyone for tuning in. I hope it's been useful. I hope that you've got something out of it anyway. If you haven't yet subscribed and stuff, please do. It does help me because I need to get 1,000 subscribers to embed live videos in my website. So that's a plea from me to get help with that. And do share this around because I do want to help as many people as I possibly can. That's why I'm doing this. Thank you very much. Stay safe. Have a good night.